Welcome to the webinar series, Decision Support Modelling, Principles and Practice. I'm Blair Douglas, Global Practice Lead for Hydrology and Water at BHP. It's my pleasure to introduce and chair this webinar. As Craig Simmons mentioned last week in introducing the first webinar, the Groundwater Modelling Decision Support Initiative is presenting a four-part webinar series with one session each week. The series explores the philosophical basis of decision support groundwater modelling and how these concepts can be put into practice. The series is presented by John Doherty and Catherine Moore, with contributions to the fourth webinar from Jeremy White. BHP and Rio Tinto are delighted to sponsor the new Groundwater Modelling Decision Support Initiative and these webinars. We see this project and these webinars as an important way of enabling a crucial and timely discussion on groundwater modelling. The GM-DSI project and these webinars will increase our understanding in the role of science-based environmental decision support, management and policy, and the role of modelling in promoting it. I'm pleased to note that there has been an overwhelming response to these webinars. We have nearly 566 people on the line today from all parts of the world, and there have already been a large number of great questions and comments raised from the first webinar series last week's, which of many, we're not able to get to address all these questions because we ran out of time. So clearly we need more time in the coming sessions. We have therefore decided to host additional webinars to answer your questions and to have a rich discussion about groundwater modelling. It'll be a great opportunity to brainstorm and toss around ideas with you all. This additional webinar will be a free-form Q&A session entitled A Global Discussion About Groundwater Modelling. We'll host this Q&A on the 17th of June. We encourage you to send your questions to us in the Q&A box during the webinar series, or you can mail us at inquiries@groundwater.com.au. We will also be sending the link during the webinar sessions. We also intend to make a global announcement to the international groundwater community about this upcoming Q&A to encourage others to participate and join the conversation. We think this global groundwater modelling conversation may be one of the world's first, so it's really exciting stuff. So today, a bit of housekeeping before John starts. Please keep your microphones and videos switched off at all times and save questions until the end. But please type them in the Q&A panel as we go, and I will moderate some of these at the end of the discussion and session. Fiona Adamson is online and will help John, myself and Kath as we navigate the webinar today. We'll be aiming to develop the series of webinars into videos that can be viewed and shared at a later date online by the GM-DSI website. You'll also receive a link today to that website shortly. I would like to thank John, Kath and the whole GM-DSI team for this interesting and important webinar series. And we couldn't do this without the tremendous support and help from Fiona from the NCGR team. So over to you, John. Thank you.
Thank you, Blair. So I will share my screen. I'll turn off my video. Okay, hello everyone. Now just be aware I'm having internet problems here today. We have a plan B, but if I start to falter, there will be remedial action taken. So this is session 2, and that's the full webinar series. So here we are at session 2. And as the title says, this webinar, we're going to develop what we started in session 1. We're going to take those concepts and fundamentals and start to explore repercussions. So this is a kind of transition webinar from the somewhat abstract webinar of last week to the quite applied webinar of next week, where we look at the tools. But here we say we have the foundation stone, we have a set of concepts on which to build decision support modelling. Let's start applying those concepts in some of the areas that are characteristic of everyday modelling. But first, so that's what's ahead, repercussions 4, and as you can see, 7 things. And then at the end of the webinar, we say, okay, if these concepts are so good, let's apply them. And we apply them to kind of look at a question that's asked all the time, When is it okay to do analytical element modelling? Like this and so many other questions, there's no right answer, but we think that there is a way to think about it. People are going to come to their own conclusions, but it's having the concepts on which basis we come to those conclusions that's important, and that's what we're trying to supply through this webinar series. So firstly, a bit of revision in case, just in the off chance someone's forgotten every detail that we talked about last week. We'll do a quick reminder. Our guiding light, our inspiration, is Bayes' equation. Modelling is all about implementing Bayes' equation. It recognises that we have at our disposal information resident in two very different kinds of data that pertain to very different scales of parameters. Data are available from site characterization and interpolation of measured hydraulic properties along geological boundaries that we think pertain to the geology, and system state, system behaviour as measured in boreholes and in base flows in rivers. The mixing exercise is done by Bayes' equation. We make predictions of management interest. We quantify their uncertainty. Our job, our mission, should we choose to accept it, is to implement Bayes' equation. And then we said that, well, that's all very well. Bayes' equation tells us what we need to do, but it doesn't say much about how. But it does tell us that it's all about information. Information has to flow from data of different types to a prediction. The more information, the less the uncertainty of the prediction. That's kind of the definition of information. But we said that this isn't going to happen unless we make it happen, and the flow of information has to be just as much a part of the conceptual model as the flow of water. Then it can begin to happen. Then we've got a solid foundation for building the rest of the decision support modelling structure. Information will always be limited. Predictions, particularly some, will have a lot of uncertainty associated with them. We said if it's all about information, then it's fundamental if we're going to do this correctly, and we'll build upon it this webinar to track the flow of information. Methods that are available through subspace methods, methodologies such as singular value decomposition, allow us to track flow of information. We said if parameters are the receptacles for information within our model, which they are, we can subdivide parameter space into two orthogonal subspaces, solution space, null space. The boundary is awkward. These pertain to combinations of parameters. Any one parameter can have 1 foot on either side of the boundary. Nevertheless, it's the boundary we've got. It's the flow of information we've got. The historical behaviour of the system can give us unique estimates of a few broadly averaged parameters. We don't know the averaging coefficients, but it can give us unique estimates of those, albeit with some uncertainty inherited from noise in the data. The null space, that must be populated probabilistically from expert knowledge and interpolation thereof. And it's the very nature of that knowledge and the interpolation process that this will be a probabilistic filling of the null space. And finally, we said that model calibration, which often in the past has an air of finality associated with it, shouldn't have that air of finality. It is one way to history match. If we do everything correctly, it allows us to make predictions whose potential for wrongness has been minimized. Not that that potential for wrongness will necessarily be small, it will have been minimized by virtue of the fact that we're placed in the center of the posterior probability distribution. If we want to explore uncertainty, however, we have to go more than uniqueness attained through calibration. We've got to fit the data lots of times with many different parameter fields, all of which encapsulate expert knowledge, all of which fit the data. Then we can look at uncertainty. Meanwhile, calibration, that uniqueness, that special uniqueness, we give it a definition, and a very particular definition. It can be a good place to go on our way to the ultimate goal, which is quantification of the uncertainties of predictions of management interest, implementation of the principles espoused by Bayes' equation. And with that revision, I hand over to Kath to start talking about our first repercussions.
So the flow of information concept that we discussed in last webinar is somewhat abstract, but it's very important. It provides us with a framework for model design, with the design goal being the assimilation of the information that matters to our prediction. In this framework, we can define 3 categories based on the prediction data relationship. This relationship emerges from the fundamental decomposition of parameter space into the solution and null spaces. Each of these 3 categories requires a very different model design approach to enable the effective assimilation of predictor relevant information. The first of these categories is when we have plenty of good measurements of past stresses and responses to those stresses, and the stress regime we're predicting in is similar to the past. In this category, the past is a good analogue for the future, and we're calling these history-based predictions. A common example of this are models used to set annual groundwater abstraction limits in areas with good historical pumping and climate records, and a well-instrumented aquifer. We can calibrate to historical observations, and an ability to fit this past data ensures that we can predict next year given rainfall forecasts. These predictions allow yearly allocations to be set, for example, to make sure that the impact of drought is spread fairly. In this category, we're designing our model to make good use of the information and the data that we have, as our forecast is best served by replicating the immediate past. A model in this category has to be both stable and fast, so it can be run many times for history matching. But the good news is we only need as many parameters as are required to fit the data. We don't need to worry about representing the null space or care about null space distortion. These models just need to assimilate the data that matters and pass this to our prediction. Black box or machine learning methods can serve this category really well, but physically based models are still useful as they provide tailor-made parameter receptacles for history matching. These models don't have to be good at predicting anything else, and in fact often they're not. And importantly, our parameter data framework shows that we can lose the advantages of being in this category, of not needing to represent null space parameter detail, if we do try and build a model to make other predictions. The other end member prediction data category is where predictions are not informed by historical observations. In this category, we may simply have no data, or we may have plenty of data, but it doesn't inform our prediction. This may be because it was gathered under an entirely different stress regime than will prevail in the future, or perhaps the data is of a different type from the prediction we need to make. If this is the case, history matching will reduce prediction uncertainty very little, if at all. So we need to adopt a modelling approach that's in accordance with this situation, and we're calling this an expert knowledge-based prediction category. Coal seam gas is one example of this, where we're subjecting our system to big vertical gradients that haven't occurred before. In this case, the information has to come from somewhere else. One approach is to give full-blown expression to expert knowledge and the stochastic nature of expert knowledge, which is represented in Bayes' equation as the prior probability distribution. In these circumstances, we're off the hook in terms of history matching because data doesn't inform our prediction. Because of this freedom, we may choose to adopt more complex models that run more slowly, and possibly we may choose to express our expert knowledge using modern geostatistical methods. These methods include multi-point geostatistics and transition probabilities, and they depict geological heterogeneity with connected low and high permeable pathways in stochastic ways. However, these geostatistical representations of geology are very difficult to adjust in the history matching process using current modelling methods. Attempts result in either a distortion of the geology or a poor fit to the data. Hence, these geostatistical methods are most useful when we're not required to history match. But this doesn't mean that history matching has no place in this category. We still need semi-realistic parameter fields. And comparing historical observations with model outputs that have been derived from our prior parameter distribution allows us to check that there's no contradiction between the data and our system conceptualization. So we don't have to fit the data exactly, but we can use it to make sure the model doesn't violate the past. As an alternative, do we need to go to so much trouble? Do we need the entire prediction probability distribution? Often, all we're concerned with is whether something bad is going to happen. This only concerns the pessimistic end of the probability distribution. If this is the case, there are cheaper ways to represent this pessimistic end. We can simply convey the worst case prediction. But this isn't as easy as it sounds. Our worst case model still has to represent geological knowledge and the repercussions of that knowledge on the prediction that we're making. However, we can do this in abstract ways, representing the repercussions of this knowledge on our prediction using simple and fast models, which still retain integrity as worst-case simulators. Often our worst-case scenario is concerned with the possible existence of a connected or disconnected permeable feature, or the presence of a flow-limiting or promoting boundary condition. So we can design a simple model that represents the possible influence of that feature on the prediction. For example, the possible influence of a connected permeable pathway on the transport of a contaminant. The worst case model may overestimate the influence of a feature significantly, but if the hypothesis of an unwanted event can be rejected, even with so many factors of safety, then it remains rejected, and the decision support role of the model has been met. And John will give an example of this a bit later. The third category, a blended information prediction category, occurs when a prediction is partially informed by historical measurements and partially informed by expert knowledge and site characterization. This is both the most challenging and the most common modelling contexts, and we have to mix data from two very different sources, and there are pitfalls everywhere in this process, as we touched on in the last webinar. Our models need to account for subsurface heterogeneity if this affects the prediction, and at the same time assimilate available data if it will inform the prediction. Examples of this category could include a mine dewatering impact assessment, which may rely both on the site characterization data as much as the historical observations of the system. So in this case, we would need to blend the information resident in these two very different sources. This blended information category requires a highly parameterized approach. We need sufficient parameters to maintain the integrity of both the solution and null spaces, to avoid any bias in our parameters and the predictions that depend on them, and to ensure that our uncertainty quantification is not underestimated. We won't go into this category anymore in this webinar, as highly parameterized history matching and the tools available for it are discussed extensively in the following webinars. So the bad news is one size model doesn't fit all. We shouldn't try to build a model to predict everything, as we'll never get there. But the good news is that knowing which prediction data category you're in, either history-based, expert knowledge-based, or blended, can help guide the model build and parameterization design process. And importantly, we have to start from the decision and then design the model with a decision-relevant prediction in mind, and consider how best to facilitate the flow of information to the prediction. And at this point, I'll hand back to John.
Okay, so I'm going to talk a little bit about reporting. I'll talk a bit now about that. and a bit about it later on. But firstly, I want to talk about some of the metrics that are used to convey the goodness of fit attained by a model, and by implication, the goodness of the model. And we'll talk about good models, bad models later. But there's hardly a report that I read these days where I don't see a plot like this. The famous one is to one line. Observed water levels, simulated water levels. The closer they are to the one-to-one line, the better the fit, and the better, by implication, is the model deemed to be. If the fit's really good, there'll be an R squared reported, and the closer this is to 1, the more bold this figures in the report. Again, the implication is, look how well I fit the past, what more do you want to fit the future? Now, even though I see these plots like this are ubiquitous, to me they mean nothing, because if we're going to take seriously the imperative, it's all about flow of information, what has this plot got to do with the flow of information? Well, maybe in some ways it does, but it's normally used instead of all the things that we really want to know. And the fit that's pursued and reported through something like this mightn't necessarily be the kind of fit that supports assimilation of prediction pertinent data. Questions that are left unanswered. Is it necessary for a model to fit everything that happened in the past? Or more to the point, every model is defective. Is it possible that perhaps there are some things we shouldn't fit because the model doesn't have the receptacles for it? And does that necessarily compromise my ability to make a prediction or quantify its uncertainty? Are there some things, if I try to fit, I can actually bias my prediction, create uncertainty which I can't quantify, and this happens because of imperfections in the model? And I'd say the answer to all those questions is yes. And getting information out of data into a model, and that's why we're fitting, not to show how good we are or to get a big high R squared. Why we're fitting is to assimilate data. And if we're taking that mission seriously, we have to be more nuanced than R squared. Now, this is a broad topic in itself, and I'm only going to talk about one aspect of it. The idea is that we ask ourselves, where is the information in this historical behavior of the system? How can I get that information into the model, and how can I do it in such a way that that flow of information isn't encumbered by defects of the model? And by taking some very simple steps, it's often possible to do that. And one of these steps is consider fitting differences rather than absolute. And I'll just show you 2 examples of this: lateral differences, temporal differences. Suppose I've got a simple model here with inflow from the right and a fixed head at the left. By fitting head data in these 4 wells, I get an estimate of transmissivity in the model domain. A high R squared translates into a good estimate for transmissivity. Suppose my model has a defect, and what model hasn't got a defect? We don't know where they all are, but by the time we take into account the coarseness of grid, the small number of layers, everything represented in the model, the processes that are left out, etc., every model's got defects. And we have to acknowledge their existence, and to act as though they don't exist isn't serving our priorities well if we're taking the priorities of decision support. So here am I now getting a pretty good R squared, fitting my 4 head measurements, and that's giving me a wrong value for transmissivity, because transmissivity is estimated as the slope of that line. The best fit through those 4 points doesn't even pass through it, and no R squared, the relationship between R squared and integrity is broken. How to get over this? Fit lateral differences instead of, or as well as, the heads themselves. In general, I do both. I don't know where the defects are, I know they exist. So if my objective function, that's the model to measurement misfit, that gets lower as I fit, is comprised of both heads and head differences, then I'm having a bet each way. Then I am laying pathways for information that bypass the encumbrances that are hardwired in to the construction of my model. The same thing applies to temporal differences. Often, the most important aspect of a model is seasonal ups and downs of water levels. Now, it could be that if the dark curve is the observed water levels and the dotted curve is my model calculated heads, perhaps I can't put the dotted curve on top of the dark curve. Perhaps there are boundary condition errors or other errors, and perhaps it doesn't matter. But the big question, again, it's the same: information. Where is the information and what does it inform? These seasonal ups and downs carry information, possibly the only information to which I have access, of the specific yield of the aquifer and of the parameters of the recharge model that provides the recharge to that causes the ups and downs. Now, it follows that if that information has got to flow from the data to the model, reproducing those ups and downs is of primary importance. Putting the dotted curve on top of the black curve is of lesser importance. And what I find, if I try it, and I have, is that if I use something like PEST, it'll roll up its sleeves and say, okay, you want the dotted curve on top of the black curve? We'll just make specific yield really high and we'll drag it up over the calibration part of the simulation, and that will give me exactly wrong value of specific yield. Instead, I can protect myself from that through saying, best, all right, try to fit the heads, but don't get too hung up if you can't. Make sure you can fit the temporal differences of heads. We will replicate the ups and downs. We will have integrity of simulation of information that pertains to specific yields and the parameters of my recharge model. Whether it's fitting differences or other strategies, and there are many other strategies we should think of adopting, the principle is the same. Where in the data set, where in the historical behavior of that system is there information? Can I process that data to distill that information? Can I process model outputs in the same way before fitting? Then fit. Process data, process model outputs, sidestep the obstacles, information flow has integrity. That is a lot more subtle and a lot more useful and serves the decision support imperative a lot better than the information conveyed and implied by the one-to-one line that adorns so many reports. And with that, I hand back to Kath again to talk about repercussions for model complexity.
My apologies. Complexity is not a black and white issue. It's way more tangled than that. To address this important issue, we have a workshop scheduled in November that's solely devoted to this important topic. How the workshop will be done is partly dependent on how the virus is managed. Model complexity is an issue that John and I and others have obsessed on for quite a while. And basically, there's no competition between model simplicity and complexity. Model complexity has to be sufficient to support the flow of predictive salient information through the model to the predictions, but it doesn't need to be more complex than that. On the other hand, model simplification can make history matching computationally tractable, but it will introduce some errors. These model simplification errors can be justified if they're small and by adopting simplification, this enables history matching to reduce predictive uncertainty significantly, and those simplification errors are small in comparison. So some practical considerations. Complex models run more slowly, and they're often so numerically sick they're in the ICU unit. Because effective data assimilation with distributed parameters requires multiple model runs, these models are not the way to achieve data assimilation. Even the efficient history matching methods in PEST and PEST++, which will be discussed in the following webinars, can't always rescue these models. While more complex models may look better when they're physically based, modelling is not about looking like the geology. It's about capturing decision salient information from that geology and the data, and then transferring that information to the prediction. If complexity doesn't serve that end, then what's the point of it? So how can we achieve this in practice? Here is a possible response for a difficult problem that comes up a lot wherever faulting occurs. Faults can both impede or enable groundwater flow to places that we don't want it to go. For example, if a model needs to simulate the effects of a bore pumping on other bores and spring flows that are located on the other side of the fault, then the fault is critical to the prediction we need to make. Because of this, it's tempting to include a fault explicitly in the model, but is this always the best thing to do? There may be some groundwater level and spring flow observations that can inform our prediction. How do we get that information into our model? And if we represent the fault explicitly, will it help us to do that? And how do we represent the lack of information when we're analysing the uncertainty of our prediction? We don't know more than vaguely the fault offset or its strike or the connectedness of aquifers across the fault. Nor do we exactly know the properties of the fault damage zone or how long the fault is. Because of all of these unknowns, we need to represent the fault stochastically. But we have a problem. If we want to use an explicit stochastic representation of that fault in our model, as each representation requires a new model grid and parameterization, this will make the assimilation of information and observations virtually impossible. The computational and manual cost of needing a new model grid and parameterization for each possible fault and then history matching it is very, very high. So a plan B is to get a bit abstract. We can focus on representing the prediction critical repercussions of the fault rather than the fault itself. To do this, we need to be able to adjust parameters that allow us to explore the repercussions of connected or disconnected aquifers across the fault and permeable features up and along the fault, as well as the parameters that represent the properties of bordering aquifers and aquitards. This requires a flexible parameter scheme, such as the pilot points that are shown, that can represent all of these possibilities. Then parameter adjustment involves both history matching to assimilate prediction salient information in our data and varying parameters under those data constraints to explore the uncertainty of predictions that may be affected by the fault. This parameterization allows aquifers to be both discontinuous across the fault and continuous either side of the fault if the data supports it. And the same continuity and discontinuity exists for aquitards. Similarly, the permeability can be high and continuous up and along the fault if it needs to be. This parameterization allows us, albeit in a compromised and abstract way, to assimilate the information in the data we have and test the repercussions of the data that we lack. It's far from perfect, but allows us to do what we couldn't have achieved with many different geometries of the fault hardwired into the model. So complexity is not equivalent to representing the truth, and hardwiring of imperfectly known geological detail, in this case faults, can hinder rather than enable the flow of the information that we have. It also hinders our ability to account for the information that we lack because of the computational burden imposed by its explicit representation. So there's no answer really as to whether explicit or implicit approaches are better. Rather, we need to remember that the goal of our model is to transfer salient information to our prediction and do this as well as we can given the resources we have. And it helps to remember that the mathematics in our models don't see the geology. They only see connectedness of permeability or impermeability. And at this point, I hand back to John.
Okay, so now repercussions for reporting. And I want to touch now on something I touched on in the Darcy lecture series last year. Now we know that when we write a report, anyone who's built a model, the thing that you want to talk about is look how good my model is. And things like the one-to-one plots that we talked about often will adorn such reports as clear demonstration of how good the model is. Now, I don't have a problem with using a report to say, look how good my model is, because after all, someone's probably paid a lot of money for that model, and they would like to be assured that it's good. Stakeholders might have to live by the outcomes of that model, and they too need to be assured that it's good. So, look how good my model is actually what a report should be about. But if that's the case, there's a couple of repercussions, and that's what this webinar is about, repercussions. There's a couple of repercussions that are not often considered enough. We've got to define good first, and defining good has to be done in remembering why we're doing the modelling in the first place. So the point I'm making here is to define good in terms of a model probably doesn't make sense. Defining good in terms of decision support that the model provides makes sense, and that can only be done really in terms of its ability to quantify and reduce the uncertainties of decision critical predictions. So good, can a model be good? I'd say no, that model sits in a vacuum. If it sits in a vacuum, it's not useful, it can't be good. It's no axis under which to project its utility. Good can only be defined in relation to why we're building the model, and that is to support decisions. And then there's another problem. Now, I don't think any model's particularly good. Good's too open-ended. I can't look back on any model with great pride and satisfaction and say that's a good model. They're all varying degrees of badness, because we can always do better, but that doesn't mean that we can't attempt to do what we have to do and no one else can do: assimilate, prediction, specific information, quantify and reduce the uncertainties of predictive interest. Good's too open-ended. Bad can be defined. So what we have to do, what our reporting then has to do, is to show that our model isn't bad. Okay, if that's the case, let's go ahead and define bad. So let's think about this logically. And I make a point of thinking about it logically because I think logical thought and modelling are often a little bit too separated. And the role of this webinar series is try to bring them closer together. So, logic. Why are we modelling? No one models for fun. We're modelling because someone has to manage a system. Okay, logic again. What does manage mean? Manage means making sure something doesn't go wrong. That means, okay, that if we accept that the focus of predictions that the model has to make, the ones of most interest, the ones that it is being built for, are those concerning whether the management is going to go wrong or not. There will be some predictions that are critically important, and on them hinge maybe the future of a management strategy. Now, if things can go wrong, and they often can, because in environmental, particularly in groundwater systems, we may never be able to preclude the possibility that something will go wrong. We're into the area of risk. Well, that's okay. All decisions are based on risk. All decisions in all areas. And what is risk? Risk can be loosely defined as the probability of something going wrong times the cost of something going wrong. And this kind, more than anything else, defines our job. Our job is to allow decision makers to know the risks that they are facing when they are deciding to do something, to decision makers and stakeholder groups. Our job is to help them define risk, and central to definition of risk is assessment of uncertainty. But we can go a little bit further than that. Okay, if we're using a model to help someone manage, and if management is all about being sure that something won't go wrong, what we have to get right is our assessment that things won't go wrong. So, if, for example, the real situation is as shown here, that's the uncertainty of a decision-critical prediction, and over here, there's a finite possibility that things could go wrong. If that's the true situation, our job is to expose it. Decisions can be made on the basis of a full assessment of risk. If, on the other hand, our modelling comes up with this assessment of the situation, where the bad thing is relegated a fairly low probability of occurrence, that is failure. So it follows that if we're going to model in a way that avoids failure, we have to ensure that the uncertainties we associate with any predictions of bad things happening have to be overstated rather than understated. It also follows that we owe it to the client, we owe it to the stakeholder, we owe it to the reviewer, to the regulator, to justify in our report why they can be sure that if we say something won't happen, then by God it won't. And the steps we have taken in creating those pathways for flow of information that allows us to make a prediction and quantify uncertainty, we have to demonstrate how every one of those steps erred on the side of conservatism rather than the other way around, so that our modelling is not a failure. And what that indicates too is that, as I said before, the model should not be separated from the decision that has to be made on the basis of that model. The model as a deliverable and then someone else uses it to make decisions, I don't see the point. How can the reporting then ensure to any interested party that when it comes to making those decision-critical predictions of what may go wrong, that we overstate rather than understate the uncertainty? Now, if it turns out that we predict something can still go wrong, there's still a finite probability of a bad thing happening, good. Infinitely better to know it than not. And, as we'll talk about next week, the modelling exercise can go further than that. If we can quantify uncertainty, we can quantify reduction in uncertainty. Therefore, the decision support modelling process can suggest what data can be gathered that can reduce the uncertainties of those critical bad thing predictions, which will then allow us to make a much better appraisal of our proposed management strategy with respect to things we don't want to happen. So on the subject of good and bad and ugly, there's model validation. This is in the traditional workflow. This is where our model gets a tick. This is where we've calibrated the model, which in the old days was seen as enough to assimilate the data. And then we validate it, and then the model's good to go. The invoice can be written, and some poor unfortunate soul gets to use the model. So this then is the traditional workflow, and in my opinion, for reasons which we talked about, this is the road to nowhere, and I hope we're over that. Our task is not about creating crystal balls or the illusions that we can see into the future. Our task is to serve the precepts of Bayes' equation, and if people are unsatisfied that after assimilation of all data using best technology, the uncertainties are still too high, well, that's bad luck for them. Better that they know it than not, and they should thank us for quantifying those uncertainties. So where does validation comes into this? I hate that word validation when it comes to modelling. Traditionally, we're supposed to divide a calibration data set into two. History match against half of it or some of it and validate against the rest of it. Now, I'm not the only one who holds this concept of validation in contempt. I happen to be in fairly illustrious company, as you will all recognise these names, some of the founding fathers of our industry. Now, just a basic consideration of Bayes' equation says, well, if Bayes' equation is all about probabilities and probabilities are all about statistics, then Statistics 101 says you can't validate anything, you can only invalidate. And then you can only invalidate at a certain level of confidence. So validation just doesn't fit into our conceptual scheme. And just to make it a little bit explicit, suppose I history match against the green dots here and then I withhold the red dots. Now, what if I run the model into the future and look, the model's not predicting what actually happened? Well, whoever said a model's going to get things right, we now know that it doesn't necessarily. You'd be lucky if it does. But still, this is not a very comfortable situation. We can go to a lot of numerical trouble and quantify the uncertainty of that prediction. We say, oh, well, I can't invalidate that model because what happened is actually within the uncertainty mantle. But this doesn't ease our disquiet with this situation, nor should it. If what this means is one of two things. Perhaps there's information, there's insufficient information in the green dots to get the red dots predicted with low uncertainty. Therefore, there's information in the red that's not in the green. Well, if that's the case, and I've actually got building this model so that I can predict further out into the future, and there's information that I've withheld from the history matching process, and if history matching is all about assimilation of information, why withhold it? This information should be in there with this information so that predictions of future uncertainty are smaller. Or we may find that perhaps if we do fit the green and the red together, as we should, to assimilate the data that's resident in all of it, assimilate the information that's resident in all the data, we may find that if we fit them together, that indeed we don't get the fit we'd like. All right, that may suggest to us that our model does need some tweaking. We may need to introduce more parameters. Or we may just have to say, all right, I've got to put up with a bigger misfit than I'd hoped with, and then that's going to be reflected in the uncertainties of future predictions. In both those cases, fitting everything all together, all the data all the time, is better than withholding some and quote-unquote validating against the rest. Now, that's not to say that you should never withhold some and see how the model performs, but what I'm saying is this notion that this should be standard practice and that this concept of validation has validity in our field is highly questionable. So, moving on, we're getting fairly now the repercussions of the modelling mindset. So, groundwater decision support modelling is fairly unique in that it sits at the intersection of a number of other disciplines. And in my experience, because of that, it's good that we can draw on the skills of a whole lot of experienced people from other disciplines, other specialities, but it also means that modelling is a bit of a battleground because each one of these people is going to visit upon us their metrics for success. And hence, we have no end of trouble in defining whether the model's good or not. And of course, this is done on an industrial scale when models are taken to court. And a lot of the arguments are simply an outcome is that we're not applying the right metrics, and the right metrics are not necessarily inherited from the metrics that would be visited on us by all the contributing specialities. So, for example, a geologist mightn't be happy unless a model is a replica of his or her vivid imagination. Well, we know from what Kat said that mightn't serve the decision support imperative the best way. An academic who studied a particular process for years mightn't feel happy unless the model embodies partial differential equations that give voice to that process in the model. The argument being, well, how can it be a simulator of what happens under the ground unless it includes those processes? Well, I hope we're convinced by now that our attempts to simulate what happens under the ground are futile, and that leaving stuff out is just as important as including stuff. It's defining the stuff that's in or out, and that can only be done with reference to the decision we're supporting. Someone who writes software that calibrates models, and I used to fall into this category. We've all modelers, we've all committed sins against humanity. I used to think I want the best fit in the world because I can get a better fit than everyone else. By God, I want that there, and I want it explicit in the report how well I fit the data. Well, that might be good for mirror, mirror on the wall, who gets the best fit of all, but it mightn't serve the decision support imperative. Bayesian mathematicians, they're such a zealot mob. They would like to see the uncertainty analysis done according to the finest of Bayesian principles, but as Catherine said last week, these probability distributions we're dealing with on highly effective simulators' hydraulic properties, we don't have that luxury. And then we come to decision makers. I need a number. Well, anyone who says I need a number is a fool unless the number they're asking for is what's the risk associated with this course of management action, and then we're into probability territory, then we're into where we should be when we come to make decisions. So decision support modelling, again, its strengths and weaknesses is it lies at the intersection of many disciplines. And if each one of the specialists from these disciplines visits upon us their expectations, then it's not going to work. We can borrow inspiration from these expectations, but we need to recognise that the expectations needed to be added, like in a vector rather than a scalar space, inherently they oppose each other unless they're combined in the way that's good for us as decision support modelling specialists. We have our own discipline with our own metrics, and we can base them in logic, and that is what this webinar series is trying to do. Sometimes it's easy. Sometimes it is all about history matching, as Kath just said, for some types of predictions. Sometimes it is all about the geology, when the history of the system says little about the future and geological insight is everything. Mostly it's hard, where we're in this difficult terrain, which we'll talk about in the next two webinars, where we're combining information of very different types that apply to very different scales. We do have our own area of expertise, and it has to be recognized as such, and that area of expertise has its own unifying principles. It has a guiding light, which is Bayes' equation. We have a metric for failure, that we don't understate the predictions that are particularly important to the management of a system. We have our roadmap. The roadmap is the flow of information. And we have our tools, which we'll talk about in the next webinars. On this basis, we have a set of unifying, consistent principles that can form the basis on which we do decision support modelling, and we have the right to our own discipline, our own study area, and we can draw inspiration from other people, other fields of speciality. We've got our own. So finally, let's put all this to practice. Let's address a commonly asked question. Just as an example, there's lots of commonly asked questions. Can I use a simple analytical element model for decision support? Well, if we're going to take anything that we've said over the last two webinars seriously, the first question we should ask is, well, it depends on the prediction. That depends on where the information resides that's pertinent to that prediction. Okay? And then we'll say, that being the case, we then undertake that logic that Kath explained earlier. We say, what's the relationship between my prediction and the information? What category does my prediction fall in that Or what category does the relationship between my prediction and data fall in? Now, following those considerations, we say, okay, what have I got to beware of here? I've got to make sure that the uncertainty of a prediction, a critical prediction, is not understated, otherwise we fail. I've got to ensure that I don't bias that prediction through history matching. Well, that biasing of predictions through history matching, that's going to happen unless we live in a highly parameterized world if our prediction is of this type. And analytical element models are not highly parameterized. So that would rule out this sphere of activity for analytical element models, but it would leave these two wide open. And let's conclude with a situation where we could use a simple model effectively in each of these prediction contexts. So, suppose that our task is to license people who propose that they want to put irrigation wells in the problem is that if they're too close to a river, they might deplete the flow in the river such that at low flows, the flows aren't high enough to maintain biotic health. Now, this is a common problem, and it's common enough that you don't want to have to build a full-blown model every time you have to answer it. So we could say, okay, worst case scenario. It's easy to build an analytical model with a Dirichlet boundary condition down the right-hand side here. We can put seasonal pumping into this proposed irrigation well. We can readily calculate a time series of withdrawal from the river. Armed with that time series, we could say, now let me take the historical flow of that river over the last 50, 100 years, time series from it, build a new exceedance probability curve, and see the probability that flow will be below a certain threshold, and how often that happens, and how long it will happen for. Fairly quickly, I come up with a pretty good worst case possibility of how low the flow will be and how long it will be that low for, and I can make my decision on that basis and move on to the next licensing application. So this would be an area where you could use an analytical element model. Now look at this other area where the past is the key to the future. So to look at that, I'll just start off with an example. Now, we've all interpreted pumping tests. So if I've got a pumping well here and I've got observation well here and here, if I use T's equation, let's assume confined conditions for simplicity, I'll get an estimate of transmissivity and storage, T1 and S1, if this is my observation well. For this observation well, I'll get T2 and S2. They'll be different. What does this mean? Surprise, surprise, the Earth isn't homogeneous. But as long as flow is roughly radial, these shouldn't be too different. They'll each be some kind of average of what's under the ground. The problem is I don't know how that averaging is done. That's the bad news, but the good news is I don't have to know how that averaging is done. History matching against each individual drawdown does the averaging in just the right way for the future drawdown in each individual well. So if I want to predict what will happen here with the same or different pumping rate, I use T1 and S1. If I want to predict what will happen in this well, I use T2 and S2 because in this case, because the prediction is so similar to what occurred in the past and the calibration process and the prediction process are very closely related, I can make this prediction, quantify its uncertainty, and the uncertainty won't be too much. Okay, let's advance that a little bit. Suppose I had two pumping wells, the red one and the green one. Suppose that I did two pumping tests. I will now end up with 4 sets of hydraulic properties, each one specific to a pumping observation pair. But the same rules apply then, provided I'm not looking too far into the future, provided flow is roughly radial. If I want to predict the future drawdown in observation well 2 from combined pumping, I could superimpose pumping from this pumping well and this pumping well, principle of superposition, with each drawdown calculated using the appropriate T and S, which links a pumping well to the observation well. And the same for this one. I could quantify uncertainty. It probably wouldn't be very much. What does each one of those T and S's mean? Some kind of averaging. I don't care what kind, but the mathematics will show for this type of prediction, if it's solution space dependent in terms of a big complex model I would build but don't have to, it doesn't matter if the parameters don't mean anything in particular. What they mean is that they're averaged in just the right way to make that prediction. Finally, then, I could apply that to a whole dewatering system, and I could have a T and an S for every pumping observation well pair. And if I update my calibration as I go along, and particularly if these pumps have different duty cycles, then I can separate the signals. I update calibration as I go along, make a prediction in any one of these observation wells using superposition of analytical element solutions based on T and S values which link each pumping well to each observation well. I can make a prediction into the short-term future. I can optimize my pumping rates. Uncertainties won't be great, and I'm making maximum use of the information that I have acquired through historical pumping, undertaking calibration with something such as PEST to assimilate that information, quantifying the uncertainty, and I'm probably doing the right thing here because of the nature of the relationship between the prediction and the observations. What I shouldn't do, definitely, is to use that model to predict drawdown anywhere else, because then we're in this territory, the blended information. This is where I need highly parameterized inversion. This is where I need to represent the null space, which sits all in here between the pumping wells and the observation wells. This is where I've got to move into a different type of modeling. So, conclusions. Well, in conclusion, especially since we've gone over time, I just repeat the unifying principles. I hope over these last 2 webinars we have given you a consistent and logical set of principles on which we can base this critically important activity of decision support modeling. We've got our light, we've got our metric for failure, we've got our roadmap, and next week we'll have our tools.